Let's move on to question number 5. It is proposed to model the number of people per hour calling a car breakdown service between the times 9:00 and 21:00 by a Poisson distribution. Explain why a Poisson distribution may be appropriate for this situation. People call the car breakdown service at an average rate of 20 per hour, and a Poisson distribution may be assumed to be a suitable model. Find the probability that exactly 8 people call in any half hour. By using a suitable approximation, find the probability that exactly 250 people call in the 12 hours between 9:00 and 21:00. So in this question, we are simply asked to explain why a Poisson distribution may be appropriate, right? So in this case, we are looking at number of people calling for a breakdown service, car breakdown service. So we can obviously use a Poisson distribution model because it satisfies the criteria that's required for a Poisson distribution modeling. In this case, what's happening is the people calling for a breakdown services happen randomly in space and time. And also that it occurs singly, right? Because one person is calling for a car breakdown service, and only one person can call at a time, right? So it does not happen simultaneously. And also it occurs independently. Irrespective of who is calling, we know that the breakdown of a car happens independently of the other. And also, we can assume that there is a constant rate of call that a company gets for a breakdown services call. So now, because these things are true, we can say that Poisson distribution modeling is appropriate. Now in the second question, we are given a constant rate, right? So we're given a constant rate of call. So in this particular case, it's 20 per hours. So this is 20 per hours, right? So we're given a average rate of 20 per hour. Now if you look at the question properly, we're asked to find the probability that exactly 8 people will call in half hour. So in half hour, if in 1 hour the call rate is 20, obviously for half hour it's 10, right? So per hour is 20, so 10 per 30 minutes, so half hour. So then for the 30-minute case, our lambda is 10. So now if we let x to be a Poisson distribution variable, our lambda is 10 here. So for this, if you want to find the probability that x is equals to 8, so we just put down the formula for the Poisson distribution where x equals to 8, and you solve this to get 0.113. That's the second question. And for the third question, we know that lambda is given to be 240. So when can we approximate a Poisson distribution to a normal distribution? So here is the condition here. So this is a condition here. So this is a condition here that a Poisson distribution be approximated to a normal distribution. So in this case, as lambda is greater than 15, then if x is a variable we have assigned as a Poisson distribution variable, then it may be approximated by a normal distribution for a new variable y, where the mean is lambda and the variance is also lambda. So in this case, we have the following situation. So here, because lambda is 240, our normal approximation would give mean to be 240 and variance also to be 240. So if that's the case, then in terms of normal distribution notation, mu is 240 and sigma is root 240. And in this situation here, we are asked to find y equals to 250, probability of y being 250. Now, because the normal distribution does not have an area for a single value, we have to make a correction here. We have to make a correction, continue with a correction here. So we say this is CC, and cols are also a discrete variable, so therefore, so then the y here, because it's a constant, continuous variable, we approximate it, we make a correction by 0.5 here. So 250 will give you 249.5 and 250.5. So standardizing it, you will get this here. So z is a standardized normal variable. So then, if you simplify it, you get this expression here, and then finally, if you look up at the table, you will get the value of this. So in this case, the value of z is between 0.613. So if you look at it in a graph like this, so the mean is 0. So it's between 0.613 and 0.678, right? So this is the area that you have to find. Okay. So that's very easy to do. You do a z less than, probability of z less than this variable here, this number here, 0.678, minus the probability of z less than this. You'll get the enclosed area. That's question number 5.